Uh, so my name is Faisal Ahmed. I'm working with Center for Sensor System at University of Siegen in Germany. So my talk is about Kalman filter-driven blind source localization for passive 3D time-of-flight imaging. So I think most of you maybe know about the concept of passive time-of-flight, time-of-flight principle. So this is my presentation outline. I will start with the introduction and giving you a recap on time-of-flight concept, and then move to the passive approach and what are the goals and problems and solution, and how we tackle the approach working with passive approach and blindly localize the source position based on different motivation points. And then I will try to show you the results and conclude my presentation. So first of all, time-of-flight camera tries to emit the signal, and reflected signal comes back to the receiver and try to get the depth information from the optical signal. So this concept is working on the active approach. So for this one, we need always active source or integrated source with the camera. But we are working on the passive approach. So let me give you the concept of passive, because passive is basically two located receivers. We don't need any additional or extra source. And that work is a passive approach, exploiting communication sources. You have heard about the Li-Fi or optical wireless. So we are exploiting VLC access point. So we have only the receiver-based system, which can give us the 3D geometry of the scene. And from there, we are trying to get the depth information. But in this scenario, the source position is unknown. In the previous case, we have the integrated source. So we know the position, the source position, and the receiver position is almost the same. But here we don't know the source position. That's why we did this one. So this idea is basically to merge two domains. Is basically optical wireless and time-of-flight imaging working independently in our current scenarios. So we try to merge and attain dual services. And this is basically a paradigm from cooperation. So existing system, what they do, they compete with the existing lighting infrastructure, which is basically a communication sources. But now we are trying to cooperate with, instead of competing with it. And this is basically the concept of giving a handshake between two technologies and getting a one other technology, which is a passive ToF imaging. So the goal is to recover the 3D geometry using opportunity illuminators. As I told you, the Li-Fi or optical wireless. So why we are exploiting existing modulated communication sources? Because when we don't need additional power requirements, and the same resources are exploited for multiple services like communication, illumination, if they are visible light range, and the sensing services. So basically the problem is source position is unknown. And when the source position is unknown, the obtained depth information always be the incorrect. So the receiver doesn't know the depth is correct or the source position is correct. So this basically generates a chicken and egg problem. So we don't know which one comes first. So we try to solve this, and also the prior works relies on the assumption that the source position is known, but this is not held in journal. So we try to solve it with the blind source localization approach. So what we did, we blindly give the instruction to the camera that it basically touches, or like maybe giving you the example of blind people. What they do, they touch the thing. After that, they recognize it. What is it, or how this is a flat surface, or what is exactly. So we are giving this sensation to the camera to touch the target and try to get the depth information and fit the model. And based on that, we try to localize the source position. So in this case, what we did initially, we were trying to use blind source localization based on random distributions. So there is always a problem when we have an initial case. It depends on always initial case. So we bring this Kalman filter into the game to localize it perfectly and based on the different trajectory values. So if you see, for suppose, if we have this source position, prediction position, so what we predict is basically depending on the initial case. So then we bring this Kalman filter. So it basically gives us the predicted value and then the measurement value, which is also random and depending on the gradient descent approach. And then we fuse it within the model and to get the correct depth information and also the correct position. So like if the source goes to the measurement and then we try to get the fusion of that, and it enables the correct position of the source. So maybe going back to this passive approach, what is exactly it is. So the source position, we know that the emitter position is unknown, and we know only the receiver position based on the bistatic geometry, which basically a 3D ellipsoidal model, which we can represent with this equation number 1, distance between the emitter and the receiver, and then we exploited this ellipsoid foci where the VLC and the ToF sensor, which is basically the emitter of the emitter position and the source position, are its foci. So we tried to localize the 3D position of the target. But what is, this is basically a bistatic algorithm. You can see the details in our paper, which is completely a derivation based on this formulation. And then how basically we simulated this whole scenario. So we exploited camera normals, and from there we try to get the correct position. Basically, we just give the correct position of the source, and then we try to generate different measurements with the trajectory of up to 10 centimeter from 9.2 to 20 centimeters range, and then we sample it in terms of the acquisition frame rate of the camera so that it can adopt according to the transition matrix, which is given by the Kalman filter. And what was the motivation behind exploiting? Because what we consider our target is always a plane. So this assumption, depending on Manhattan world assumption, that says that every object or every plane is perpendicular one of the axes of the single coordinate system. So let's give you the example of our indoor infrastructure. Most of the target always have a surface. So we exploiting this assumption in our approach to get the 3D geometry of the scene and also the localization position. So how this helps us? So we exploit this assumption, and then we try to what we are getting. So it's always an incorrect depth, but what we are getting, we try to fit the model and then update with the gradient descent approach. After that, we try to get the incorrect emitter position, because we give the incorrect position, and then this loop goes onwards until the range of this. And then from there, the cost function always gives us. So cost function, the key takeaway is we don't use ground truth values in our cost function. So we always, depending on the defit, which we call it a fitting model, and from the incorrect depth information, it corrects the cost function, and from the correct cost function, we have the pseudo-measurements, which basically gives us the emitter position in each iteration of the Kalman filter until we reach the complete trajectory. From there, we move the location of the source until the direction that we move, and after that, we push this cost function until to get the converge it to get the correct position of the source. And so in each step, we have the Kalman gain. And once the Kalman gain is updated from the previous measurements, and then it updates the covariance matrix and from covariance matrix and state matrix, and also this until reaching this trajectory source location, what we get until that range. So let me give you the whole algorithm structure. So first, what we did, we initialize the first initial guess within this range. After that, these propagation state and covariance matrix adopt those values. After that, it goes to the plane fitting process. Within that, we have the inverse problem and try to solve it. After that, we get this pseudo measurements depending on the bistatic algorithm. And these pseudo measurements is given to the Kalman filter gain, which adopts this. And after that, we try to update the state and covariance matrix, and until we reach the final trajectory point. So like try to find the local minima with using this gradient descent approach. And we have this innovation function where we exploited this like a pseudo random measurement process, because we don't rely on the ground truth. Sorry. So these are the simulation results where we try to get, so in the ground truth values, we try to this sample it because of our trajectory. So based on these samples, and then we have a pseudo-measurement. And if you see the estimated bistatic algorithm, depending on that, we try to make with the ground truth values. So this way, because in the previous case, what was happening, we were depending on the random value, but now we give this assumption our probabilistic approach so that it can cover the next step. So we have the covariance matrix. So because it's not always we know the measurement error and covariance matrix, so we try to like it's learned by heart. Like giving the example of Mars rover, basically they don't know, they try to use different covariance matrices to reach the correct position. And depending on the emitter position error and the cost function value, we try to different iterations we show here. So we try to achieve a minimum error in the emitter position of 0.5 centimeter, and also the cost function goes up to near to the 0 values. So this way we try to correct the depth information and correct the source position without having access on the ground truth. So maybe let me show you the ground truth value. We have the plane, and then this is the incorrect depth information. So the plane shape, because depending on the source position where the signal comes from, so this shape is incorrect, and the depth information, if you can see, 25 centimeters, and then what we estimated is almost the same with the ground truth. And these are the incorrect depth errors where we have until 14 centimeter, but now we have only 0.5 centimeters in maximum. And these are the comparative results. So in this paper, like this one is presented in EU CITIUS conference, where we only exploited the random blind source of localization approach, but we don't use the Kalman filter process in it, and now we use it. Then we are able to get the 0.8 centimeters error in total, and then the depth error is 0.5 centimeters in the depth reconstruction. So let me conclude my presentation. So this is basically a blind source localization algorithm where we try to jointly recover the position and the depth estimates. And this is the first work where we use for this passive approach, joint localization and sensing. And this proposed approach combines the gradient descent approach and in our plug and play. So we plug this Kalman filter process into this gradient descent approach to get this bistatic geometry. And our results are almost 97% accuracy in simultaneous source localization and depth recovery. And this work is adopted based on the Kalman filter. And our next target is to exploit in real experiment where we have a target, which is basically a plane, or in anything which can be transformed into the plane for this. And thank you for your listening. And I would like to thank you to European Union funding this project.